Hello and welcome to IGCSE Physics. We're going to look at lenses in Chapter 7, page 156 to 161. So, after today's lesson, you will be able to describe the action of a thin converging lens on a beam of light, use terms principal focus and focal length, draw ray diagrams for the formation of a real image by a single lens, draw and use diagrams for the formation of a virtual image by a single lens. Describe the nature of an image using the terms enlarged, same size, diminished, upright or inverted, and use and describe the use of single lenses and a magnifying glass. And lastly, show understanding of the terms of a real image and a virtual image. Okay, so the first thing that we're going to look at is a converging lens. A converging lens is a lens that converges the light rays. So if we look on the left, we see that all the light rays come in parallel. That is as if light is coming from a far distance. Okay, and then if it goes through a converging lens, it focuses, okay, the beams to one central point. We call that point the principal focus, as seen on the left, and the distance between the lens and the principal focus is called the focal point. Okay, so if we just go through the terminology, the yellow thing in the middle is called the lens. Okay, we have the principal axis, which is basically the middle of the lens, and then we have the focal points. Okay, and for practical use, we indicate also twice the focal points, or the primary focus. That is the focal place where the rays would come together at the focal point or primary focus. Okay, now very important in this to understand lenses and what we're going to do, we're going to need to know what's the focal distance. Okay, and that depends on the thickness of the glass and the curvature of the glass. And secondly, it will also be useful to know twice the focal distance when we start drawing the diagrams. Okay, so we also have our object. So if we represent our object with an arrow, and then we'll find that on the other side of the lens will form a image, except for one type of scenario where the image and the object would be on the same side. Okay, so how do we find our image? The first thing that we do is we draw a ray parallel from the tip of the arrow parallel to the axis up to the lens. From there, the refracted ray goes through the F, the focal point or the primary focus on the other side. Second step is we'll draw the second ray through the center of the lens. We call that the optic center, and we extend it straight through. Its refracted ray is symmetric, so it's just a straight line. Okay, and then the third ray we draw through the focal point or the primary focus on the left up to the middle of the lens, and then the refracted ray goes parallel to the right. And if you can see where all three of these rays come together, that is where our image would be formed. Okay, so you know the position of the same point, on the image. Okay, so if we look at the tip of the arrow, we can find the position of the tip of the arrow. If you're looking at the center of the arrow, let's say the yellowish part, we will find the position of the yellowish part. But we're going to, for all practical purposes, just be looking at the tip of the object. Okay, so here is an illustration of what happens if we move it closer and closer. We get the image increasing up to equal size, then enlarging, and then we get it on a similar size. Now what we have here is a simulation from PhET Simulations. We see the object on the left, it's a pencil, so ignore the frame, and we see the image on the right. Okay, we see the crosses where the focal points are, and now what we will look at firstly, we'll look at the diameter. So if we have many rays coming through, okay, the diameter of the lens, or basically the size of the lens, determines how many light rays goes through. Okay, but we will only be looking at our principal rays. There's obviously more light rays. Okay, the refractive index, that's just the type of glass, the thicker or the less thick the medium, will determine how close or how far your focal point is. Okay, and then obviously the curvature, if it's a thick lens or a thinner lens, will also depend on it will also affect the focal point or the primary focus. Okay, so we've now looked at our three rays. We've got our ray at the top, which is our first ray. We've got our ray through the center, which is the second ray, and the third ray. And all three of these rays will always line up. Okay, so in this point, we will see now the difference between the different locations. The first thing that we're going to do is we're going to start with a object that is far away from the focal point, behind twice the distance. Now if you can see where my cursor is, that's about where the second or twice the focal distance would be. The moment where the object is far away from the lens, more than twice the focal distance, we will find an image that is reduced in size. We will see that the object is the image is upside down. We call that an inverted image, and the object is a real image because real rays come together to form that image. These rays are actually there. So as we bring our object closer to our focal point, we see the image is increasing up to a point where we reach the point where it's twice the focal point. And on twice the focal point, our image is still inverted. It's still a real image because real rays come together, but now it is of the same size. Okay, and then if we move between twice the focal distance and the focal distance, we see that our image becomes enlarged, still inverted, still real. Up to the point where we go and we put our object on the focal point. Now, if the object's on the focal point, we will see that the rays are parallel to each other and they never come together anymore. Now, if we move the image even closer, we see these green lines, and these green lines are not real rays. Okay, so we'll see virtual rays that is reflected backwards, and what we see now on the left is a virtual image. It's not really there, it's just virtual, and it's because the rays that is not real rays. Now this example is an example of a magnifying glass. When you read through something like on a piece of paper, the image looks bigger, but it's not really there. Okay, it's a virtual image. So the rays are just drawn backwards, okay, in the opposite direction, and then we basically get our virtual image. Okay, so there are 3 points that's important. Behind twice the focal distance, we get a smaller image. On the second twice the focal image, we get a image of the same size. Okay, between the focal distance and twice the focal distance, we get an enlarged one. And if it's between the focal distance and the lens, we get a virtual image that is upright. Okay, so these are 4 different images that you need to be able to draw and describe. So here we just look at them again. As we move our object closer, we see the image is increasing up to the point where it's enlarging, and then when it's close to the lens, we see the rays backwards bringing together our image. Okay guys, and that is it. Here's just a little picture of showing you the difference between different focal points and lens widths. Okay, we can see how even on a photo the quality and the focal length actually makes such a big difference in the photo of the same guy. So I hope you have an awesome day, and if you've got any questions, please let me know.